This module will discuss the biomechanics concept of torsion. Problem 1 asks, what type of external loading produces a spiral fracture? As you can probably guess, the correct answer is torsion. Torsion is a type of mechanical stress whereby the external forces twist an object about its longitudinal axis. Therefore, torsion is the external loading that produces a spiral fracture as seen in the image to the right. I will now apply a torsional load to the chalk, and you can see that there is a spiral fracture produced. Tension, also known as tensile stress, would be an incorrect answer because it is an external loading that occurs when two forces pull on an object, such as bone, in opposite directions so as to stretch it and make it longer and thinner. I will now produce a tensile load. I will pull the chalk in opposite directions. You can see that there's no spiral fracture. Compression is also an incorrect answer because it is an external loading that pushes or presses an object so as to make it shorter and thicker. Here is an example of a compression load, which is actually the strongest loading force. You can see that I can't even break the chalk. Bending is an incorrect answer because it is an external loading caused when there is a compression force on the side the object itself is bending toward and a tensile force on the opposite side. This is an example of a bending load. You can see that there's no spiral fracture. Shear stress is the last incorrect answer because it is an external loading in which two forces act parallel to each other but in opposite directions so that one part of the object is moved or displaced relative to the other part. I will now apply a shear load to the chalk and push it in opposite directions. You can see that there was no spiral fracture produced. Problem 2 asks, when a cylindrical bone is subjected to a torsional load, the maximum tensile load is generated in a plane that is at what angle to the long axis? The correct answer to this problem is 45 degrees. Stress is defined as a force acting over an oriented area at any point in a body. Stress is denoted by the symbol sigma with a subscript of the face direction followed by the applied force direction. If a vector pointing outward from a face on an object is in the same direction as the force applied to that face, then it is considered a normal stress. If a vector pointing outward from a face on an object is perpendicular to the applied force on that object, then it is considered a shear stress. The overall equation to solve for maximum tensile stress is given by the following equation. Normal stress in the x-x direction plus normal stress in the y-y direction divided by 2 plus normal stress in the x-x direction minus normal stress in the y-y direction divided by 2 times the cosine of 2 alpha plus the shear stress times sine of 2 alpha. This may seem like an intimidating equation, but in order to solve problem 2, we do not need to memorize this equation. Since normal stresses are due to tension and compression, and question 2 asked about a force subjected solely to a torsional load, which is a type of shear stress, we can eliminate the terms in the maximum tensile stress equation that have normal stresses and only keep the terms relating to shear stress. Shear stress in a cylindrical object such as bone that is under pure torsion is equal to torque times the radius of the cylinder divided by the second polar moment of area, denoted as J in the equation shown. Knowledge of this equation is not necessary, but I provided it for your convenience. To prove that the maximum tensile stress is found at an angle of 45 degrees to the longitudinal axis, we can just assume that shear stress is any constant numerical value. Since the maximum tensile stress is a function of sine, and we know that the maximum value of a sine function is 1, we can easily prove that at 45 degrees we will obtain our maximum tensile load. When we plug in 45 degrees to the maximum tensile load equation, the angle is multiplied by 2, becoming 90 degrees. Sine of 90 degrees is 1, and thus the constant value of shear stress is multiplied by 1. When we plug in 0 and 90 degrees into our maximum tensile stress equation, the equation yields a tensile stress of 0. Logically thinking, this makes sense because a stress applied either parallel or perpendicular to the object will produce a tensile load and not a torsional load. When we plug in 30 and 60 degrees into our equation, the angles of the sine function become 60 and 120 degrees respectively, and our equation yields a constant value of shear stress multiplied by the square root of 3 divided by 2. Since the square root of 3 divided by 2 is less than 1, multiplying the shear stress constant by that value will give a tensile stress less than that achieved at 45 degrees. In this graph, the maximum tensile stress equation was used with a shear stress constant being 1 for simplicity. We can again see that for tensile stress, the maximum value is achieved at an angle of 45 degrees. I also included the graph of maximum shear stress for comparison so that one can see maximum shear stress due to torsion occurs at 0 degrees. This is because maximum shear stress is a function of cosine and not sine. Thank you for listening to this module on the biomechanics behind torsional loads. I hope you enjoyed it.